Then welcome everybody. Thank you for being here. Today I will talk about process-based life cycle sustainability assessment of waste management system. And I will talk mainly about how we use Modelica to provide sustainability indicators in our waste treatment systems. I'm Julie from EPFL. I'm doing a PhD, and I'm here today with Manuela, Jana, and Jaroslav. We are all four working in the R&D of Kanadevia Inova. Now to the content. I will introduce briefly what are the challenges around waste treatment, then the methods we apply, typical results that we achieve with our decision support framework, and then on perspectives and challenges with the decision support tool we are developing. Starting the collaboration, just a word, we are between academia and industry. We are working with EPFL, the laboratory of François Maréchal, since 2020. The Kanadevia company is active in waste treatment systems, EPC, engineering, procurement, and construction, mainly for waste to energy, anaerobic digestion, carbon capture. And now they are expanding the portfolio to operation and maintenance, life cycle solutions, raising a lot of different questions, and we are collaborating with the laboratory on specific waste treatment systems and systemic approaches to analyze them. You might imagine a waste treatment system a bit like this. Here you see a typical flow sheet that we have in our tool. Waste to X, why do I write X? Because there are so many typical products that we can achieve, commodities, not just heat and power, but metal recovered, fuels that are produced in liquid form, gaseous form, so many possibilities. And here I want to show typical questions that we encounter. We can start just with the solid waste that we usually have, municipal solid waste. What are the fractions that are in it? Where do we sort it? When do we do it intermittently? What fractions do we want to sort out? Just the metals, the plastics fractions, just the PET. These waste fractions fluctuate by region, in time. Then on typical process engineering questions, okay, how do we design our system the best way possible? How do we integrate it in the more general framework systems around? Then when we talk about integration, we may look at heat and cold utilities, possibly also power. And when we look at power and renewable energy, we want to look at renewable power production. We may then need to look into storage. What fraction do you want to store in solid form of the waste, or do you want to store the finished product? And then three overarching questions that are the relations to markets, uncertain by nature. This is the business case, economics. Then you have the question on environmental indicators. How do you want to select the indicators to have the environmentally least burden system? And then one of the pillars that is least regarded, but also important, the social indicator. The workers, what are the conditions? What is the impact of your system on the local communities? And these three aspects form so-called sustainability pillars, and they form very often conflicting objectives. And this is why a tool is needed to decipher what are the performance of our systems in these conflicting objectives. Now, from a company point of view, why do we need a tool to do this? How does it crystallize in real? It's because from the R&D, so we're in the R&D, we have so many ideas, typical strategies, trends in the markets, and then we want to establish specific roadmaps with product specifications, and the jump is quite big. And this is why we came up with this tool. We call it DSP for ROSE, Decision Support Platform for Resource Optimization and Sustainable Energy. It's in two parts, and today I'll focus more on the second. The first one is helping us on ideation, deciphering from many different pathways. And the second one is using Modelica, assessing interesting options, going more into the detail of the design. From an academic point of view, why did we not take something that already existed? There are more than 100 frameworks for waste frameworks for decision support. Here, I want to show for 8 selected good publications how they satisfy 6 requirements that we defined as critical for a tool. The first one is systematic traceability of the data. Second is consistent architecture of the tool, interfaces to stakeholders, and the software, of course, with modules. Third one, pretty straightforward, open source tools for the collaboration with industry. Academia is simply much faster. Multi-domain modeling here, it's mainly three aspects. Dynamic systems, we need to be able to represent the thermodynamics for the chemical processes. And the third aspect, specifically for waste, we need to be able to represent the heterogeneous flows in the details that are specific to each stakeholders. Once it will be ultimate composition, once it will be rough physical composition, macro composition, we need to be able to represent this flexibly. Fifth, we talked about environmental, economic, social indicators. And then sixth requirement, we want to be able to represent these indicators in a multi-objective assessment to weigh the indicators. And here, the point is that we didn't find a tool that was satisfying all of these requirements, and this is why we developed a new one. So now on the methods, maybe a first general background. How do we assess innovation in these treatment energy systems, and more specifically waste treatment systems? You start, and this slide is the life work of my professor, so I had to include it. We start with defining our systems, input, outputs, conversion technologies. To have done this, you go to the typical flow sheeting systems. You integrate your systems in the process, in the systems, integrating typical resources. Most common one is the heat through pinch analysis. Then, once you have many of these processes, you might have different pathways for converting input, and you might start to have superstructures with many options to treat this input. And in the end, you want to compare all of these options in a multi-objective assessment. Today, I show mainly these four aspects that are circled here, that are covered by our tool. The middle ones are covered by the first part of the tool that I'm not showing today. So this is the general picture, and then how does it apply to our specific tool and architecture? Starting by system definition, we have an interface with the stakeholder, with OpenModelica, OpenModelic, to the database we are developing inside of the company. We are building the interface. We then define our models in OpenModelica for the system integration, flows integration. This layer provides all the inventory for the life cycle analysis. We can analyze our indicators and integrate our system with the Python interface and interpret results. And this Python interface also provides these indicators I was talking about. Here may be interesting to look at are the three pillars that we find. I don't know the three pillars. This is the life cycle impact assessment. We follow ISO standards, equally for the social pillar. This layer typically is just taking the inventory and providing the indicators. You might think of life cycle impact assessment. The most knowledgeable known indicators is global warming potential. And then you assess them in multi-criteria analysis. With this, we see already three requirements that are covered: the open source, the consistent architecture of the tool with clear interfaces to stakeholders, and in the software with defined modules and interfaces, and then the sustainability metrics. Now, if we look at how it's built a bit more in detail, main topic of this conference, Modelica. We use OpenModelica just because it's open source. And there we define our whole library for waste treatment technologies. And of course, we had to come up with conventions for variable naming, physical units, code structure to interface it later on. We have also for the streams, all of our commodities and direct emissions to the environment are defined with specific flow variables and rules for attributes. Then Each of the models also provides process analysis structures, typically for exergy analysis. And then, of course, for the indicators I was talking about, environmental flows, accounting, social layer. And then, of course, completing this multi-domain requirement, we have the thermodynamic packages that are included here, reported data from the OM chemical simulator in our platform database. And then very important, of course, is how we document our models. There we have very specific schemes on what is documented, how it is checked. And this is how we define our building layer in Modelica. Then maybe, so then here we also have this consistent data requirement satisfied with this version instance. Now, how do we interface this in Python? I thought this might be interesting in this scope. So here, very simple workflow, just using packages for Modelica system, Modelica REST. We, every step of the way, report the data that is used, record sheets for the model documentation also, satisfying, again, this systematic data retrievability. And then you might see this feedback loop. When we want to do parameter sweep, we used it when we are fitting some of our processes to existing plants. We had the case where we fitted an electrolyzer. And here we use, for now, very simple black box optimizer, but already giving some results for the multi-objective assessment. But for now, very, very simple. And then continuing on engineering workflows, I will not illustrate these today, but as I said, we have very systematic version checking of these models to increase the stakeholders' trust. Then more on engineering approaches, we have the pinch analysis and heat exchanger network design to integrate best our systems. And then the last bullet points is linking, maybe if you remember the first part of our tool, I said I wouldn't talk about it, but this is bridging to this first part of the tool, the linearization. We pass all of our library into a linearization. We can use these black boxes then essentially in this more superstructure optimization for pathway identification. Now maybe a last word on the methods. The interface to users, so key for a tooling industry. We define three types of users. The one decision maker that has access to the data and the results through the reports. Then intermediate, the kind of collaborators we have from other universities, but maybe also from our mother company. We choose fixed and engineering workflows, people that just need to rerun several times, but that don't need to go into refined systems. And then, of course, the ones that are editing the code source on different levels. And there, of course, with the hierarchy, we are increasing the knowledge integration. And with this comes user expertise, but also more time investment. And with this, I close the methods parts and I go to those typical results. Today, really qualitative, just to show you what we have generally. This is a typical system we have. Here for the illustration, I took a system that treats municipal solid waste in a sorting first step of sorting. You see here manual sorting linking to the social layer, because who wants to sort by hand? This is a very, very active topic of discussion. Then automatic sorting technologies, here sorting out metals. And then more on the chemical engineering, so incineration, flue gas treatment, then power generation with the water steam cycle, superheater. Then for the CO2, we have a carbon capture unit based on amines absorption. Such a system here, just for illustration, takes as input waste, and this is how we typically define waste. So around 50 attributes, which are, as I said, macro and also ultimate. And we define rules on how to define these attributes. Then, with the Python interface, first thing we can do, okay, mass and energy balance. And we see here more than 100 compounds we track across these simulations. Typically, you can show the macro like this, but then you really want to also go more into the detail. For example, checking carbon flows. And this is typically seen through our consistent data sets linking. We can in one click retrieve the ultimate composition of any of our systems. But then you might also want to look at specific systems. Here, the carbon capture was a subsystem, and this bar here is actually a whole embedded system. And here we are blending out the macro components, just looking at the oxidized products and checking how the amines degrade. And so you have really process details. You might want to do the same on energy. Here, illustrating on the composite curves for heat integration. And this typically helps to see how best integrate your systems and how to recover energy better. Then we talked about optimization. Obviously, we are not just doing snapshot analysis of steady state processes, but we might have dynamic simulation. Here in this case, when we are linking to renewable energy production, power from wind and solar generation, with storages that fluctuate. And you might ask yourself, okay, how to size the storage. Here, using this simple optimizer, we can evaluate the KPIs we selected for several scenarios and look at specific scenarios. Here in this case, you see quite technical process-oriented indicators and the topics. But what if you want to go more into the detail of the breakdown of these topics, not just aggregated indicators? This is the value of linking to Modelica, is that we base everything on the inventories provided by the simulation in Modelica. Here I show just an out selection and extract of the units included. We can see how they relate in the breakdown of the cash flows. So we have really more insights in the system performance. And here, again, snapshot analysis. So what happens if I look at this specific system for one of the costs that was a major contributor, the operation and maintenance cost here. I see that it's actually linked to the maintenance periods in my system. In this system, I assume that the number of workers will increase, their retribution also. So we see the impact of process failures, for example, here, not just on economics, but also on social impacts. But of course, so many other indicators can be used for the social indicators. And then last illustration of the sustainability indicators, environmental indicators, also called life cycle impact assessment. Here I show indicators for human health area of protection, but you might understand this A here, climate change, human health, long-term fossil, as global warming potential impact. And we see, of course, without too much surprise, that the CO2 is the main contributor. You see on the legend that's we have the inventory of the direct emissions. And of course, this is for gate to gate when you have your plant. But what happens with all the commodities that upstream or downstream also generated impacts? And this is also linked in Modelica. We have, through the structure that I was talking about, the links to other databases like EcoInvent. And here I can see how my direct emissions relate to all the other downstream and upstream systems that I maybe didn't model because they already existed in the other database. That's for the... Yes, and of course, I mean, this is important because you can avoid burden shifting. And this closes the sustainability indicators I wanted to illustrate. And with this, I can go to the takeaways. With this platform, we cover these 6 critical requirements that we identified. We work with other universities and company, mainly our mother company, on specific projects, also going into tendering activities. Then on the challenges, there are so many challenges. One, of course, typical in the Modelica is debugging of large interconnected systems, but then, of course, onboarding new users. We are thinking of many ways to do it, but yes, how to do it efficiently. And then a general trade-off between flexibility and consistency. And then also on the interpretability of the results. I mean, you saw these 3 indicators, but how do we convey them the best way possible to the stakeholders? Because every stakeholder has a different view. And then on perspectives, so many perspectives, but one thing for sure is the interface on different levels, on the database to the workflows, the results. And then on features, we are looking at joint analysis of heterogeneous CA, but also going to the dynamic optimization, doing it a bit better than what we have now. And with this, this is the end of my presentation. Thank you very much for listening.